All right, so in each study below, determine whether the groups are paired or unpaired. So for the first one, the two study the effect of women's tears on men. Levels of testosterone are measured in 20 men after they sniff women's tears and after they sniff a salt solution. The order of the two treatments were randomized, and the study was double-blind. Now, for this one, you're talking about the same men sniffing the women's tears and sniffing the salt solution. This is paired data. Now, suppose that we try to do this same study, but in this case, to study and to investigate the effect on women's tears on men, 40 men watch a romantic movie and then half sniff women's tears and half sniff a salt solution while their brain activity is monitored. Well, essentially you have 20 men doing one thing and 20 men doing the other, two separate groups. This is unpaired. All right, so for this lesson, we'll consider a difference of two population means, mu1 minus mu2, or the difference of the two means, under the condition that the data are not paired. For instance, a teacher might like to test the notion that two versions of an exam are equally difficult. He could do so by randomly assigning each version to students. If he found that the average scores in the exams were so different that he could not write it off as chance, then he may want to award extra points to students who took the more difficult exam. So the teacher would like to evaluate whether there is convincing evidence that the difference in average scores between the two exams is not due to chance. So when the conditions are met, we are ready to test whether the difference of independent, unpaired means is significantly different from zero. So in this case, is the difference of unpaired means is equal to zero or not equal to zero? And as with all the other difference tests we've been looking at, for our class, the null value for the unpaired test will always be 0. As for the point estimate, the teacher would need a best guess for the differences based on the sample data. So that best guess is the point estimate, and it's the difference of the two sample means. So you find the average for one group, the average in the second group, and then subtract. So x1 bar minus x2 bar is a point estimate for mu1 minus mu2. The difference of the true difference of means. Okay, as for the conditions, the t-distribution can be used for inference when working with the standardized difference of two means if the two conditions are met. First, each sample meets the conditions for using the t-distribution. That is, independence and normality. But we also have to have a condition that the two samples are independent of each other. That is, they're unpaired. So for instance, if the teacher believes students in his class took the test independently of each other, exam scores followed a normal distribution, and the two groups of students taking the different versions were unpaired, then we can use the t-distribution for inference on the point estimate. So the standard error looks a bit more complicated than the last couple lessons, and that's because essentially it's a combination of the standard errors for the two groups. So the formula is the square root of the first standard deviation squared over that sample size, plus for the other group, that standard deviation squared over that sample size. So S1 and S2 are the standard deviations of the two groups, and N1 and N2 are the two sample sizes. So for instance, to calculate the standard error for the difference of two means, the first sample had 21 observations with a mean of 12.6 and standard deviation of 3.2, and the second standard deviation had 30 observations with a mean of 17.8 and standard deviation 4.1. Okay. So what's important, square root, I take the standard deviation of the first sample, so 3.2 squared, divided by the first sample size of 21, plus the other standard deviation is 4.1 squared, divided by the other standard deviation, the other sample size, 30. So that comes out to be a standard deviation of 1.02. Now, as for degrees of freedom, Technically, it's a very complicated formula, as you can see. So, because we use a t-distribution, we need to identify appropriate degrees of freedom. Technically, this is the formula. Have fun. That said, we're going to be using a different formula, one that's traditionally taught in books. So, an alternate formula, and the one we will use in this class, is to use the smaller of the two sample sizes minus 1. So, N1 minus 1 or N2 minus 1. So, that's the method we'll be using in the samples, examples, and the exercises. So, for this test, we take the smaller of the two groups, whichever group is smaller, take that sample size and subtract 1. And although this is a different formula than this, it's really going to have much impact on the p-value. So we'll stick with the simpler version. So for instance, if you want to estimate degrees of freedom for the difference of two means, if the first sample had 21 observations with a mean of 12.6, standard deviation 3.2, and the second sample had 30 observations with a mean of 17.8 and standard deviation of 4.1. Well, one sample is 21, the other sample size is 30. The smaller sample size is 21, so degrees of freedom we'll use is 21 minus 1, 20 degrees of freedom. So we have 20. The actual degrees of freedom, if you're using that more complicated formula, the actual degrees is 48.34648047. So we're going with a smaller degrees of freedom. And is that going to increase or decrease the likelihood of a type 1 error? Well, recall, type 1 errors occur when the null hypothesis is true, but we reject it. And you only reject when you have enough evidence to reject. So our estimate was 20. The actual is 48. That means we're going with less evidence than we normally should have. So that would decrease the likelihood of a type 1 error. So we're less likely to reject an hypothesis with fewer degrees of freedom. That would mean that the likelihood of type 1 error is going to decrease. Type 2 errors are going to be more likely, but a type 1 error is less likely.